Well, it's pouring outside, so let's try another video. In a previous video, I tried to answer the question whether or not the moon was moving towards the Earth or the moon was moving away from the Earth, but because Google gave me two contradicting answers. So with some formulas and some numbers, we were able to answer that question in the other video. So have a look at that one if you're interested. Of course, like if you can calculate all that stuff for the Earth and the moon, you can also calculate the same stuff for the Sun and the Earth. And you use like a similar set of formulas, just some other numbers. Just plug them in there and see what type of result you get. Okay, that's a bit of fun. Taking it like one step further, what about like some other star out there in our galaxy or in the universe? And maybe that star has like some exoplanets like orbiting around it. So here's the question. If we know how long it takes for the exoplanet to make one orbit around that central star, and we know the distance between that exoplanet and the central star, can we then somehow calculate the mass for that central star? Okay. Now the only thing I've changed on this slide compared to the previous slides, where in the previous slides it said R here, R, and R. Here I've changed the R into an A, but for the rest it's all the same, okay? So A is now the distance between the central star and the exoplanet. Let's have a look at some formulas. So here, we've seen this one before in the other video. mv squared over A, the centrifugal force, must equal gmm over A squared, and that's the law of gravitation. If you multiply both sides by A over the mass of the exoplanet, yeah, I'm saying that correctly, then you get like A over the mass of the exoplanet times the centrifugal force equals A over the mass of the exoplanet times like the law of gravitation. Of course, you can cancel out all those equal terms, so this A cancels out that A, and this m exoplanet cancels out that m exoplanet. Not a lot will be left. Okay, so the left side of this whole equation, only phi squared is left there, not a lot. And the right side of this whole equation, only gm central star over A is left. So basically, you end up with this formula, and the formula says the speed of an exoplanet depends on the mass of the central star and the distance to it. That's basically what it says. Yeah, so the speed of an exoplanet depends on the mass of the central star and the distance to that central star. Okay, we can live with that. Then next, we need to cover something very quickly. It says here, if a circle has a circumference length of 10 meters, and you follow the circle at 2 meters per second, that's your velocity, meters per second, then how many seconds does it take to make one full orbit around the circle? The circle is 10 meters, you're walking at 2 meters a second, of course it will take 5 seconds. Yeah? So that 5 seconds is then called a period. Of course, the circumference of a circle is 2 pi times the radius. So the formula then becomes like, the formula for the period becomes the period equals 2 pi r, yeah, the length of the circle divided by the velocity around the circle. That's what we're doing here as well. Now, the only thing that's changing here, of course, we don't use r, we use A. Okay, we labeled that thing A, the distance between the central star and the exoplanet. So the formula turns into P equals 2 pi times A over V, the velocity. So far there? So far okay? Next slide. So we get like two interesting formulas. We have the phi squared equals gm central star over A. And we also have like the period equals 2 pi A over V. Now you can rewrite this. You can rewrite this part. If P equals 2 pi A over V, then V equals 2 pi A over P. That's how it works. So this part here goes there, where it says phi squared. So you get like 2 pi A over P squared. Of course, like 2 pi A squared is 4 pi squared A squared, and P becomes P squared. So you get this. Yeah. Still equal to gm central star over A. Now you can cross multiply. What do I mean cross multiply? 4 pi squared A squared times A must equal therefore P squared times gm central star. So you go like that, and it must equal that. And that's what I'm doing here. That's this outcome. So P squared gm central star equals A times 4 times pi squared times A squared. Of course, like a times a squared becomes a to the power of 3. Then you divide both parts of the equation. You divide both parts of the equation by gm central star. So that will cancel each other out on the left-hand side. So you end up with p squared equals 4 pi squared a to the power of 3 divided by g mass central star. Okay, that's the formula. This one. Okay, that's a cool formula. We see that here. Yeah, that's a cool formula. So it says this time, this formula is all about the time it takes for an exoplanet to orbit its central star. And that time depends on the distance to the central star. This one, the distance to the central star. And also the mass of the central star. Yeah, so the period is depending on the distance to the central star and also the mass of the central star. Of course, like in this whole formula, we have a lot of like constants. I mean, 4 is a constant, will never change. Pi squared is a constant, will never change. The gravitational constant is a constant, that will never change. And even the mass of the central star typically doesn't really change. So the only two real variables here are the period and the distance. Okay, so let's start to rewrite a little bit. So this is our original formula. What I'm doing here, I'm just moving this a to the power of 3 in front of this whole part. That's what I'm doing here. Yeah. Then I'm dividing both parts of the equation by a to the power of 3, which will cancel out on the right hand side. So you end up with like p squared over a to the power of 3 equals 4 pi squared over gm central star. Now you can flip them on both sides if you want to. So flip them. So I just flip these two. So a to the third goes up and p squared goes down. And same thing here, 4 pi squared goes down and gm central star goes up. Why am I doing this? Because 1 over 2 equals 1 over 2. True. But that also means 2 over 1 equals 2 over 1. That's still true. And you can even see it better when you start to cross multiply. Because p to the power of 2 times gm central star must equal a to the power of 3 times 4 pi squared. But if you flip those values, it still says the same thing here. It still says e to the power of 3 times 4 pi squared must equal p squared times gm central star. Nothing has changed there. Hopefully you see that okay. Okie dokie, next slide. But that means we have this interesting equation. But that's actually Kepler's third law. How cool is that? We've just discovered Kepler's third law. Johannes Kepler. His law says the ratio of the square of an object's orbital period with the cube of the semi-major axis of its orbit is the same for all orbits orbiting the same primary star. Yeah, that's like the explanation. Okay, let's assume that the central star is our sun. Okay, and our exoplanet is the Earth. Of course, like our Earth, well, how long does it take for our Earth to make one orbit around our sun? Well, it takes 1 year. Okay, and what's the distance between the sun and our Earth? It's 1 astronomical unit, 1 AU. So if you plug those numbers in up here, so 1 to the power of 3 divided by 1 to the power of 2, well, 1 times 1 times 1 still equals 1. And here, 1 times 1, well, still equals 1. 1 over 1, that's also 1. So this whole thing, well, turns into 1, basically. So it now says 1 equals g, the mass of our sun, divided by 4 pi squared. Cool, we know that. Next slide. So we have two interesting formulas. We have like this one. Yeah, so where you see, or you can actually recognize like Kepler's third law. And you have this one, where we plugged in some of our values for our sun, our own star. How do we combine them? Let's start on the right hand side. If I rewrite this, I can actually move m sun in front of this whole part. So I move this thing there. So I get like 1 equals m sun times g over 4 pi squared. Then I divide both sides by m sun. So 1 over m sun equals this whole thing over m sun And of course, like m sun will then cancel out. So it says 1 over sun equals g over 4 pi squared. But if I look at this part of the equation, if I look at this other equation here, this other formula, if I take this m central star outside, or in front, or or here, it doesn't really matter, okay? So you get like this formula, this one, this equation. But you can see this part is the same as that part. But that part here is the same as 1 over the mass of our sun. So let's just plug the 1 over the mass of our sun in there, in here. Yeah. So you get this. You get like a to the power of 3 over p squared equals 1 over the mass of our sun times the mass of the central star. But then it says like, this is just multiplying. 1 times the mass of the central star is just the mass of the central star. So you end up with like a cubed over p squared equals the mass of the central star over the mass of the sun. But that's a ratio. That's just a ratio. It just means that like, okay, I can calculate the mass of a central star in units of solar masses. And that's what it says. That's pretty cool. Let's do that. Let's try that. So, one more thing very quickly. Of course, like if we set the mass of our sun to a convenient value of 1, so if we make this value 1, something over 1 is always that something, okay, and I plug in like 1 for the astronomical unit part here. I plug in 1 for the years part here, and 1 for the solar mass here. Look at this. You get like 1 cubed over 1 squared equals 1. Yes, 1 over 1 equals 1, 1 equals 1. That is true. Makes sense? Yeah. Next slide. Okay, so now it becomes more serious. If an exoplanet orbits a star with a period of 83.6 days and a distance, or at a distance of a quarter of an astronomical unit, then what is the mass of the central star? So we've got this formula. Okay, we've derived that one from a whole bunch of other formulas. We can plug in those numbers. So you plug in the quarter of an astronomical unit here, and you plug in the number of years here, because like 90 days is roughly a quarter of a year, I guess. You calculate all that stuff. You get this number. So you get like it's like roughly 1/3 of a solar mass. That's the whole thing. Yeah, or 1/3 solar masses, you can say. And of course, a solar mass is this number. It's a really big number, which is basically 2 times 10 to the power of 30 kilograms. So if you multiply this number with that number, you get roughly 6 times 10 to the power of 29 kilograms. And we've just calculated here, the mass of the star, I think you pronounce it Gliese, okay? Using the data from the exoplanet observed, known as Gliese 581d or 581 delta. How cool is that? Just by playing with some formulas and playing with some numbers, we are now calculating the mass. We are able to calculate the mass of a very distant star. How cool is that? Yeah? Okay. But what? What if? There's always a what if. What if the observed exoplanetary data is not available in astronomical units and years, but is given to you in units of days and kilometers? Okay, you mean, well, what then? Well, we know that like 1 AU is roughly 150 million kilometers. Yeah, that's this number, to the power of 3. We know that 1 year is roughly 365.25 days. So you do the calculation using Excel or your calculator, and of course you get this number. Yeah, so 2.5 times 10 to the power of 19 km over years. But we've been given the data, we've been given like Gliese's data in like units of days and kilometers. So if we need to calculate the number of kilometers, if it's like a quarter of an astronomical unit, that's 0.25 times 150 million kilometers, that equals 37,500,000 kilometers. Of course, the days is still days. Yeah. You plug in those numbers again, and you get this number. Using your calculator or using your trusty Excel. But that's in kilometers per day. So here comes the trick. You've got this number. You now multiply by the inverse of that number. Yeah, so you have this number in kilometers per day, and you need kilometers per year, so you multiply by the inverse of that number here. And what do you get? Guess what? You get this number. And this number, of course, 0.298255, if I do a page up, well, that's this number again. So now we're able to simply multiply again by the mass of our sun, and as an output we get the mass of our star. Our star out there, in this scenario, is Gliese, the Gliese star. Yeah? How cool is that? So, I mean, that's the reason why physics and mathematics are absolutely awesome. I mean, you play with some formulas, you chuck in, you plug in some of the numbers, and all of a sudden you can calculate stuff that's maybe like millions, if not billions of light years away from you, and you can actually calculate the mass of like some distant stars. How cool is that? Anyway, hope you've enjoyed this video. Let me know if I need to make some more. I'm just having some fun here because it's raining outside. Bye bye, Marco signing off. Bye bye.